Hello everyone. This next video we are going to be looking at the idea of an expected or a mean value for a particular type of probability, the expected value of the outcome of a chance event um, in terms of either outcomes or involve like a game of chance, or in other cases like how the average value um, can be calculated from a series of essentially random events. Um, our goal here is to think about what happens if you have something that happens repeatedly and has a chance to be different values. What is the overall average result, and what does that mean as far as decision making goes? So this really kind of picks up where we left off in terms of um, what we were doing with combinations and permutations before. So we will approach this kind of as a continuation. So let's imagine, if you will, that we are back playing the Connecticut Lottery again. As before, we are looking at our chances of winning. We know from our previous work, let's get this going here, that we have 44, oops, pen, hello pen, and there we go. We have 44 C6 combinations. That is 7,059,052. Um, so the idea is, we're picking 6 out of 44 numbers. That's the total number of combinations. So what's the likelihood that we actually win? The probability that we win is equal to 1 over 7,059,052. So here's my question. If we play this lottery, how large does the jackpot have to be before it's considered a fair bet? Well, I suppose we'd have to know how much we pay for a ticket, right? The ticket is $1. So the ticket is $1. So how large would the jackpot have to be for this to be considered fair? Now, for the moment, we are going to ignore the fact that you actually do get money if you match less numbers of numbers. So while you do get the jackpot of at least $1 million, if you match all 6 numbers, um, if you match 5 numbers, you actually get about $2,000. And if you match 4 of 6, you get, I believe, $50. We're going to ignore that for now, just for the purposes of calculation. We'll come back to that with a later problem. But for now, we're just going to focus on the jackpot. How large would the jackpot have to be for this to be considered fair? Well, the jackpot would have to be large enough to overcome all the times that we lose, right? So again, think about this in terms of odds. The odds, if we were to do this, the odds would be 7,059,051 to 1. So we would have to have a jackpot of at least that much because we are going to lose this many times. So the jackpot would have to be at least this number or higher. Therefore, the jackpot would have to be greater than 7,059,051. In other words, it's got to be this number or higher, right? But that kind of makes sense because the ticket is $1. If the ticket were $2, we would need 2 times this. And that really kind of makes sense because if you take this number, 7,059,052, and you divide it or multiply it by the probability, you'll get exactly $1. Okay. So the question then becomes is what happens in the case that we don't have this jackpot, right? What if we have a jackpot of, say, $1 million? Okay, so in $1 million jackpot, this is where it starts. When somebody wins, the jackpot is reset to $1 million. So at $1 million, what would happen is we would win $1 million this often. So if we do that, if we do 1 million times 1 over 7059052, we're going to get a value of, hold on, let's take out the calculator here, 1000000 divided by 7059052, about 14 cents. 0.14166. 14 cents. So that means in the long run, if we play for $1, we play a ticket for $1, we are going to get back an average of 14 cents for every ticket. Now keep in mind that that's a long run average, and since our chances of winning are 1 in 7 million, this is a very, very long run average. So think about this as if it were 10 million. If it were $10 million, and I'll change to green. If we had a $10 million jackpot, then the value per ticket would be 10 million times this. So just move that over 1 decimal point. And so you'd have about $1.42. And so what would happen is if the jackpot were actually $10 million, your $1 ticket would get you an average of $1.42. So this is more than fair. But does this mean that you need to go out and play the lottery every time the jackpot is over $7 million? No. And the reason for it is pretty simple, that in order to really make use of this, you'd have to buy a lot of lottery tickets. We're talking at least 6 million. If the jackpot were 10 million and you spent $6 million on lottery tickets, you'd have about an 87-88% chance of making a $4 million profit. That is before taxes. So even 10 million probably wouldn't be enough. The jackpot would have to be probably closer to 20 million before you saw a really appreciable profit, given taxes, lump sums, things like that. Anyway, this is the meat of what we're trying to get at right now, is this value right here. This is called the average value or expected value. And in a case like this, it doesn't make a whole lot of sense because it's not like each ticket is going to give us $1.42. Could you imagine that? Could you imagine if every single ticket did this? That we played, the lottery would go belly up. So clearly this doesn't happen, but this is an average. All right. So let's look at a few other situations of how this can apply as well outside of lottery, because there's a lot of really good applications for this. Okay, so first off, let's look at the definition. So we're going to formalize what we just did. And this is called the definition of a mean of a random variable. For ease of terms, we'll call it expected value. Okay. The idea here being that is what we expect as an average for each chance event that happens. And this is equal to the sum of all x's multiplied by the probability that it happens. So what this is telling us to do is x is all possible outcomes. List of outcomes. And then P of x is the probability that each event happens. So what we're going to do is we're going to make a list of all the outcomes that can happen when we have a chance event. We're going to find the probability of those happening, and then we are going to multiply those and then add that all together. and that's going to create this average value. It sounds a little complicated. It's not as complicated when you actually go to use it, and it's a little bit more common sense. Let's take a look. So one common example I like to use with this has to do with driving tests. And so don't I don't hold back in saying that, yeah, I took a couple tries to pass my driving test. Don't stigmatize it. It happens to the best of us. Hey, you know what? Depends on your instructor. Just like failing a test in class. Sometimes you don't do as well on a test as you'd like, so you go back and retake it. And the same is true for your driving test. If you don't do as well on your driving test, you go back and you retake it. So not everybody passes the driving test the first time. So we've compiled some statistics, and we have the following. People can take the driving test as many times as they wish. Now, although I'm hearing now that rule might not be completely true now, that you may have a certain waiting time before you have to try again. But let's say 86% of people pass the test the first try, and that's this first line here. So 86% of people pass the first time, 10% of people pass with 2 tries, 3% pass with 3 tries, and 1% pass with 4 tries. And we're going to assume that nobody takes more than 4. Essentially 0. They're out there, but they're very, very rare. Okay, so here's my question that we would ask. Now, the DMV would want to know, in terms of resource allocation, how many tests it should expect to give. So let's say during the summer months, they hand out 100 learner's permits. So let's do this. So let's write this down. 100 learner's permits. Okay, so for those 100 learner's permits, they would want to be able to give a certain amount of tests. Now, they're not just going to book 100 tests. Well, yes, I suppose they will book 100 driving tests for that, but some of those people are going to fail. And some of those people are going to have to come back and take the test again. And the DMV will need to anticipate this because they need to have the cars handy, the instructors handy, the supplies, the logistics, the money. They need to have all of that set away so that everybody can take the driving tests that they need. So let's take a look. Again, we have 100 people. So let's say that those 100 people fit in right with this table. And so now we can actually just go ahead and very easily, oops, I'm making marks here. Let's erase. Okay, so now we can say, well, 86% of people passed the first time. Okay, well, 86% of 100 is 86 people, right? So how many driving tests will these 86 people take? They will take 86 tests. So 86 tests will be enough for these 86 people. Now, 10% of 100 is 10. So 10 people will take 2 tests each. They'll fail the first one, pass the second time. So how many tests will they take? They'll take a total of 20 tests. 3%, well, that's 3 people. They'll need 3 tests each. That's a total of 9. And this one person, they're going to need 4 tests. So the idea being that we want to know for each column how many total tests are being performed for that subgroup. And the total, will add it all up, and you're going to get 119 tests. So those 100 people, those 100 learners permits that were handed out to those 100 people, they are going to end up taking ultimately 119 total tests as an average. So how do we translate that into a per person argument? We do this by dividing by 100. There is 100 people, and so we have an average of 1.19 tests per person. Now, what's the usefulness of this number? Well, the driving learner's permit season that people go and get their learner's permits from, it's not always going to be 100 people. It could be 140, it could be 200, it could be 183, whatever it is, right? But we know that we can set aside tests according to multiplying by 1.19. So if it's 1.19 tests per person, let's say we have 183 people, 183 times 1.19, and they should expect to give about 217, 218 tests to 183 people. That's the power of that number. And they will make sure to have those supplies on hand. Maybe a few extra for logistics, just in case of, scheduled appointments, or, that one group of people that just can't seem to pass their tests, whatever it is. That way, we have an indication. Here's a great way. This number is 1.2 approximately. 1.2 is 6 over 5. So I can, nice thing I can do here is say that this is approximately 1.2, 6 to 5. So we can say that this is 6 tests for every 5 people. And this is the idea of expected value. We can use this to estimate what each individual person will do on average. Given, even though it's going to be random, this is how it will tend in the long run. So the idea being that you could get some people, like a group of people, just, hey, boom, 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 all pass, all pass, all pass. Wonderful. And so maybe the average is close to 1. But then, if these numbers are true, if these probability values are all true, then eventually you're going to start seeing people that take multiple tries, that they'll need to schedule multiple tests, and then the average will start to creep up. And if these numbers are true, you are going to get close to 1.19. Okay. Here's another situation where this can have some useful impact as well. Let's say the number of courses that a student at a university is registered in. We're going to do much the same thing. But now we're going to take a little bit of a shortcut, okay? So we could think of 100 students, all right? And we could think of 100 students, 1,000 students. These numbers are all two decimal places. 100 students would be fine. But let's go back to this one for a second, and I want you to look at what happened. We used 100 people, which means I multiplied these decimals by 100. But then to find the average, I divided by 100. That's interesting. So why bother? Why multiply by 100 only to divide by 100 later? That's a really good question. We don't have to do that. Let's try skipping that. So we're not going to think, we could think of this as 100 students. So we can multiply by 100, but then divide by 100? No thanks, let's skip that. Okay, so what we're just going to do is we're going to ignore the fact of thinking this is 2 students, 3 students, 9 students, and we're just going to multiply. We're going to multiply 1 times 0.02, and we're just going to write those values down. So we have 0.02, 2 times 0.03, that's 0.06, 3 times 0.09, that's 0.27, 4 times 0.25, hey, that's 1. 5 times 0.4, that's 2. 6 times 0.16, that's 0.96. And 7 times 0.05 is 0.35. Okay, so let's see what these numbers represent. This is the likelihood that you have a student registering in a certain number of classes. As you can imagine, when you go to college, you're going to be registered in a few courses at a time per semester. Most of you may not know how many courses to select. They'll tell you, but generally the number is 5. For most majors, you'll on average take like 5 courses a semester. And that's a pretty standard value. 3 credit courses, about 15 credits a semester. So you end up taking about 5 classes. If you're lucky, some semesters you could take 4. Depends on the classes you're in, or even if you're taking like you're doing like physics classes or big science classes with a lab that are 4 credit courses, you might get away with taking 4. Um, but there are some people that have to take more, especially things like music majors, which have to take like many classes with many different instruments. So you could very easily be taking 6 or even 7 courses uh, per semester for those. Just as the same as you could have students on the low end. So you could have students on the low end taking no commuters, right? Or maybe part-time. So this represents kind of like the share. And as you can imagine, you know, this people with 5 credits seem to make up the bulk of the discussion here. Let's add these together, and we're going to add these together, and you're going to get 827 plus 8. So that's 0.35, 3.35, 4.31, 4.66 courses per student. That's what this number represents. This number represents an average of 4.66 courses per student. And so the idea is college would like to know that like most students seem to be hovering near the 5 credit mark, but there are a few that take more and a few that take less. And this could dictate anything from like how many instructors to hire, how much space to allocate for classes, things like that. So you can see how this could be very useful. Okay, let's take a look at some other situations. Okay, here's another interesting one. Um, Again, we're going to go back to talking about games of chance and whatnot, and then how to combine this with the things that we already know. Okay, in a school, let's say we have a raffle, and we're setting up a raffle of 1,200 tickets. They're sold for $5 each. One of the tickets will be a $2,000 winner. Joy of joys. That's a big prize. For this raffle, I'd say that's a big prize. And then further, 6 more tickets will be a prize of $300. Wow, okay, this is a good raffle. No other ticket is a winner. What is the amount we expect to win if we buy a ticket? Okay, so let's take a look. So we basically want to know what is each ticket worth. So on average, if we look at the total prize pool, what is the total prizes that are out there, and then we can divide that into the amount of tickets. Okay, so you can think of this as either a probability or as a total. Um, we can think of this as, if we think of this as probability, right? So going by the way that we did it before. So 1,200 raffle tickets are sold for $5 each. One of the tickets is a $2,000 winner. So what outcomes, we purchase a raffle ticket. What are the outcomes? The outcomes, the first outcome is we win $2,000. And what is the probability that we'd win that? The probability there is 1 out of 1,200. Furthermore, what's another prize? 6 tickets will be a prize of 300. That's also an outcome. What's the likelihood of that happening? Looks like 6 out of 300. 6 out of 1,200, I'm sorry. 6 out of 1,200. So let's see what happens. We're basically, those are our outcomes, and then everything else is a 0. So when you have an outcome of 0, we're not really going to worry about the calculation, because when we multiply by the probability, I suppose for completeness sake, is 1193 out of 1,200. When you multiply by 0, it's just 0. So let's go ahead and do this. We have turn on the calculator, 2,000 times 1 over 1,200, 1.66 plus, oops, my plus key does not appear to be working. Many keys are starting to fail on my keyboard, and it's rather scary. Okay, so plus, now we win $300, and the probability of that is 6 out of 1,200. And the total then is 3.16667. Okay, so another way to look at it, so the expected value is $3.16. But here's another way to look at it. Again, 1,200, right? So the denominator is 1,200. So just like we did before, you can think about it when in terms of um, just like the original problem with 100 people at the DMV, we can think about this in terms of the total prices across the 1,200 tickets. And so what are the total prices? The total prices are 2,000, I mean, plus 6 times 300, and that's a total prize pool of 3,800. And that $3,800 of total prizes split onto 1,200 tickets is approximately $3.17. So the idea is, on average, our ticket is worth $3.17. Now, the tickets sell for $5. So this is important because now when the tickets are sold for $5, the school is going to keep the remaining money. So when we find the expected value, it's important for us to know that, like, if we're doing a raffle or a carnival game or something like that, that the amount that the price needed to pay has to be enough to overcome the odds if we're the one running the system. So in terms of you, the player, is this a fair bet? No. But in terms of you, the fundraiser, then yes, it's in your favor because you're selling the tickets for more. So when you do this, obviously, higher price means more money coming in, but you want to be careful. There's a sweet spot because if you sell the tickets for too much, no one buys them. So you want to sell them for just a little bit over expected value. Or what you can do is you can choose the value, sell the tickets, and sell the tickets for a price that you think people would be willing to pay, and then kind of think about what the prices would be afterwards, assuming you sell all the tickets. You can always adjust if you don't sell the tickets. So, like, what if they don't sell all 1,200 tickets? What if they sell, 950 tickets? Can you change these numbers? Sure, based on expected value. Okay, so this is how it works, and the calculation never really gets any harder than that. Let's do one that's slightly more complex and kind of puts everything together. And this one involves combinations. Okay, there is a game in Connecticut that is fairly recent in the last few years that's called Kino. Okay, Kino is a game that is essentially it's a lottery game, but it's played in a casino. So picture um, a lottery, like balls coming out of the lottery bin, just like we did before. Um, but instead of a game playing once every, I don't know, once couple times a week, like we do with the lottery or Powerball or anything, um, this happens once every 5 minutes. So imagine a brand new lottery game once every 5 minutes. So it's kind of like mini lottery. But to compensate for that, you're choosing between numbers from 1 to 80. So it's a much larger pool of numbers. Order, again, is irrelevant. Okay? So the type of game we're going to look at is called four-spot Keno. A player pays $1 and selects 4 numbers from between 1 and 80. That's a huge range. The game organizers, so here's the thing though, which makes it unique. The game organizers will then randomly select 20 of the 80 numbers. So you're not selecting just 4 numbers. The game organizers select 20 of the 80 numbers, and your job is that your 4 numbers were 4 of the ones that were picked. That seems more accessible. That almost seems easy. Almost. But I think we should do the probability to find out. This is tantalizing, isn't it? And this is why this game is so popular, because on the surface they're like, you're selecting 20 of the 80 numbers and you have to match 4 of them. I can do that. It feels like that's like a 1/4 probability. As you can imagine, it's not. Let's look at the amounts. If you match 0 or 1 numbers, you get nothing. If you match $2, you get your number back, or 2 numbers, you get your dollar back. If you match 3 numbers, you win $4. Therefore, profit 3. So profit 0. You win $4, profit 3, and you win a profit of $1.11. Okay, so you pay $1 for the ticket, but then you get, some money back. Okay, 4 numbers match $112. That can't be that hard, can it? So here's my question. As you can imagine, we want to know what's the expected value of our ticket. That means we're going to have to do some calculations, okay? So again, 4 numbers, selecting 20 of the 80 numbers. Let's do some math. So we want to know, first off, let's start with the easy one. What's the probability that we match 4? Okay. So we're going to match 4, right? But we're picking 4 numbers. We are picking any 4 of the 80 numbers. So remember that probability, as we discovered in our last unit, probability is equal to the number of successes out of the number of total events. Okay? So we want to know how many successful matches that we get if we're matching 4, what's considered a success, and then out of the total. Well, again, we're picking 4 out of 80, right? So when we're picking 4 out of 80, 80C4. So my denominator is going to be 80C4. What's my numerator going to be? Keep in mind that there are 20 good numbers, right? And we are hoping that the 4 numbers that we pick are 4 of the 20 good numbers. So my numerator is 20C4. So it's 20C4 over 80C4. So that is, let's do it out, 20 C4. So that is 4845 over 80C4. 1581580. I felt like that number was going to be higher. 158, is it? Yeah, 1581580. But still, the probability that we match 4 is a bit smaller than you would have imagined. The probability of this happening, we'll actually do the division. 4845 divided by 1581580, 0.003, so 0.3%. It's harder than it imagines. That's why the probability is the amount is set the way it is. Okay. Another way to think about it is each number has a 1/4 chance approximately of being a good number. So it's 1/4 times 1/4 times 1/4 times 1/4. And as you can imagine, that's a pretty big number. Okay, that is 1 out of 256, which is approximately what that is. Okay, it's a little bit different than that, but it's approximately that. Okay, but what about matching 3? Okay. Actually, let's do match 0. Likewise, what's the likelihood that we match none of the numbers? Okay, let's think about this. We're matching none of the numbers. Again, we're making a selection of 4. Okay. We're making a selection of match 4. So let's see, matching none of the numbers. That means all 4 numbers were bad numbers. How many bad numbers were there? 60 bad numbers. Because 20 of the 80 have been chosen to be good numbers, 60 of which are bad. So we're saying that if we're not matching any, we have 4 of the 60 bad numbers. And we can go ahead and do that calculation. But we actually don't have to really do this one because, again, the idea is we get nothing for this. But the reason why I did it is because I wanted you to realize that when we have a bad number, it's one of the 60 bad numbers. So I'm actually now going to erase this. I'm going to erase this, and now we're going to look at the situations that we need, and that is 2, 3, and 4. So let us now do the likelihood of matching 3. Okay, so again, we're selecting 4 numbers, right? So the probability, we're going to match 3 out of 4. So what would that be? Now, again, think about it. We're matching 3. That means 3 must be good, so 3 must come from the good numbers, and 1 must come from the bad numbers. And it must come from the bad numbers. It can't be a match, a 4th match, because then you'll fall in the one that we already did. So we're saying that you've matched exactly 3 out of 4. You only win this prize when you match exactly 3 out of 4. You don't get this prize in addition to the match 4 prize. So 3 good, 1 bad. So again, both have to happen at the same time. That's going to mean we multiply. And so that's going to come out to be 20 choose 3. We're choosing 3 of the 20 good numbers and 3 of the bad numbers. Or sorry, 1 of the bad numbers. And we're going to divide this by 80C4. Now, 60C1 is just 60. But the thought is the same. And what I can then do is go ahead and I'm going to go ahead and write this in. And I'm going to use the actual notation for this. Because now then it would be a simple case of changing the notation, changing the numbers to fit the next one. 60C1. And that's 68,400 over 1581580, and that is so I'm just going to go ahead and 60 NCR1, and we're going to divide it by parentheses 80 math NCR4. About 4%, 4.3%. Let's do, yeah, well, let's do 4.32. Yeah, let's make it 325. So 4.325%. Okay. Likewise, probability we match 2 out of 4. So same idea, right? But this time we're choosing 2 of the good numbers and 2 of the bad numbers. So what's going to change? Just the parts that we choose. 20C2 plus 2 of the bad numbers all over 80C4. And I'm just going to go ahead and do that calculation rather than writing it out. I'm just going to go back, change that to a 2, change that to a 2, and we hit enter, and we get 21.26%. Okay, so there's a 21.26% chance that this will happen. Hey, not bad. That's pretty good. That's going to happen with a fair, regular basis. Okay, so now let's actually go through and find the expected value. So again, we want to know, you can do this in two ways. You can do this with the amount that you win, or you can do this with your profit. If you do this with the winning amount, you just have to remember that this, you'd also just subtract 1 for the fact that you paid $1 for the ticket. And that's usually the way I like to do it. So I'm just going to go ahead and do it that way. Otherwise, then, hey, if we do that, then we wouldn't really have to worry about that either. But for purposes, we'll just go ahead and do it that way. So you win $1. It's $1, right? It's $1, then $2. No, 1 4 112. Okay, so when you match 2 tickets, there's this. So it's 1, you win $1, 0.2126 of the time. Plus, you win $4, 0.04325 of the time. Plus, you win $112, 0.003% of the time. Let's go through and find that out. And so you end up with 1 times 0.2126 plus 4 times, oops, plus key doesn't work anymore. I wonder why. So plus 4 times 0.04325 plus 112 times 0.003, and we get a value of 7216. Your ticket has an expected value of 7.7216. That basically means that you will pay $1, but you will get back 72 cents on average per ticket. Is it fair? Of course not. No casino game is fair. Is it worth playing? That's for you to decide. But this tells you exactly how unfair it is. And it turns out you lose about 27 cents. So on average, you would lose in the long run about 28% of what you went in with. So if you go in with $100 and you play Kino for a while, expect to leave with about $72 if you stop at a random spot. There you have it. And so that's how expected value works and what you can do with it. Okay? I hope this was enjoyable. Some interesting kinds of problems. And I will see you in class sometime. Have fun.